Right now, as you watch this video, something extraordinary is happening that almost nobody thinks about. The data that makes up this video, every frame, every pixel, every second of audio, traveled to your device through a system so vast and so precisely engineered that it makes every other communications network in human history look primitive. And almost none of it is wireless. Most people imagine the internet as something that floats, something in the air, something invisible that surrounds us and connects us without any physical substance. That picture is almost entirely wrong. The internet is one of the most physically substantial engineering achievements in human history. It runs through cables, real physical cables, buried under oceans, stretched across continents, running into buildings, and the engineering that makes it work at the speed and scale it does is more remarkable than most people ever consider. Let's start with the scale. There are currently over 5.4 billion internet users on Earth. Every single day, those users generate approximately 3.5 quintillion bytes of data. That number is 3.5 followed by 18 zeros. Every email, every video, every message, every financial transaction, every search query, all of it moving through the same physical infrastructure simultaneously, continuously, at speeds that were considered impossible 30 years ago. The internet is not one network. It is a network of networks. Thousands of separate networks run by governments, corporations, universities, internet service providers, all connected to each other through a set of agreed protocols that allow them to communicate regardless of their individual architecture. The system that makes this possible is called the Internet Protocol Suite, and it was designed in the 1970s by Vint, Cerf, and Kahn. Their fundamental insight was that data didn't need to travel as a continuous stream. It could be broken into small pieces, sent independently through whatever route was available, and reassembled at the destination. Those small pieces are called packets. When you send a message or request a web page, your device breaks the data into packets, typically around 1,500 bytes each. Each packet contains the data itself, the destination address, the source address, and sequence information, so the receiving device knows how to reassemble everything in the correct order. The packets then leave your device and begin a journey that might take them through dozens of different physical locations before they arrive at their destination. The first stop is your router. Most homes have a router, a device that connects your local network to your internet service provider's network. The router receives your packets and forwards them onward. This forwarding process is the fundamental operation of the entire internet. Every router on the network maintains a routing table, a constantly updated map of which direction to send packets to get them closer to their destination. Routers don't know the complete path a packet will take. They only know the next best hop. Each router passes the packet to the next router, which passes it to the next, in a chain that continues until the packet reaches its destination. This process happens billions of times per second across the entire internet simultaneously. The routing decisions happen so fast that a packet traveling from London to New York, a distance of 5,570 kilometers, might pass through 15 or 20 routers and still arrive in under 100 milliseconds. That is less than a tenth of a second. Now consider where those packets actually travel physically. When you watch a video hosted on a server in the United States from a device in the United Kingdom, your data crosses the Atlantic Ocean, not through satellite, through a cable, a physical undersea cable lying on the floor of the Atlantic Ocean. There are currently over 400 active undersea cable systems crisscrossing the world's oceans. Their total combined length is approximately 1.3 million kilometers, enough to wrap around Earth more than 32 times. These cables carry over 95% of all international internet traffic. The satellites you might imagine carrying your data are used primarily for remote areas where cable infrastructure doesn't exist. For the vast majority of global internet traffic, the cables on the ocean floor are doing the work. These cables are engineering achievements of extraordinary scale. A typical modern undersea cable is surprisingly thin, roughly the diameter of a garden hose for the deep ocean sections. But inside that thin exterior is a precisely engineered structure. At the center is the optical fiber, hair-thin strands of ultra-pure glass through which laser pulses carry data as light. Each fiber can carry multiple wavelengths of light simultaneously, a technique called wavelength division multiplexing, with each wavelength carrying its own stream of data. A single undersea cable might contain 8 or more fiber pairs and carry over 200 terabits of data per second. That is 200 trillion bits of data moving through a cable thinner than your wrist every single second. The light pulses carrying that data degrade over distance. The ocean is deep. The cables cross sections where the ocean floor is over 8,000 meters below the surface. Every 50 to 150 kilometers along the cable, a repeater amplifies the optical signal, compensating for the degradation. These repeaters are powered by electrical current running along a copper conductor inside the cable. Electricity sent from shore stations thousands of kilometers away, powering devices in complete darkness at the bottom of the ocean. Landing these cables requires extraordinary logistics. Cable ships, specialized vessels carrying enormous spools of cable, deploy undersea cables at speeds of around 8 kilometers per hour. A transoceanic cable deployment can take weeks. Once landed, the cable comes ashore at cable landing stations, often nondescript buildings on coastlines that contain some of the most critical internet infrastructure on Earth. From the landing stations, the data enters the terrestrial internet infrastructure. Inland fiber optic cables carry traffic between cities. These cables run through conduits buried underground, along road corridors, railway lines, waterways. In major cities, the fiber density underground can be extraordinary. In London, New York, Tokyo, the underground conduit networks carrying fiber cables are vast. Eventually, your data reaches a data center. Data centers are the physical location of the servers that host websites, applications, and services. They range from small rooms to enormous facilities covering tens of thousands of square meters. The largest data centers, hyperscale facilities operated by companies like Google, Amazon, and Microsoft, contain hundreds of thousands of individual servers consuming hundreds of megawatts of power. Keeping those servers cool is a major engineering challenge. Data centers use sophisticated cooling systems. Air cooling, liquid cooling, in some cases entire buildings designed to draw cold air from outside environments or cold water from nearby rivers or the ocean. When your packet arrives at the data center hosting the service you requested, the server processes your request, assembles a response, breaks it into packets, and sends those packets back on the reverse journey. The return path may be completely different from the forward path. Routers continuously adapt to network conditions, sending packets through whatever route is currently fastest and least congested. The speed at which all of this happens is genuinely extraordinary. A modern fiber optic connection can transmit data at speeds approaching 2/3 the speed of light. The physical limitation is not the electronics. It is the refractive properties of the glass itself. The laser pulses travel slightly slower through glass than light travels through a vacuum. Engineers working on ultra-low latency networks are experimenting with hollow core fiber, cables where the light travels through air inside the fiber rather than through glass, which could reduce latency by approximately 30% compared to conventional fiber. The security of all this data moving through physical infrastructure around the world is maintained through encryption. Before your data leaves your device, it is encrypted, scrambled using mathematical algorithms that would take conventional computers longer than the age of the universe to break without the correct key. The encryption and decryption happen so fast, in milliseconds, that you never notice them. The last section of the journey is what engineers call the last mile, the connection between the internet service provider's network and your home. This final link has historically been the bottleneck. Copper telephone lines, cable television infrastructure, cellular networks all have lower capacity than the fiber backbones carrying traffic across continents and oceans. Full fiber connections, where optical fiber runs directly to the home, are progressively replacing older last-mile technologies and are capable of delivering speeds that saturate most devices. What you end up with is a system of extraordinary complexity, packets of data leaving your device, traveling through your router, along underground fiber, across the ocean on cables a garden hose wide, through repeaters powered from thousands of kilometers away, into data centers containing hundreds of thousands of servers, back out again along a different route, arriving at your device reassembled in correct order, decrypted, displayed, in under 100 milliseconds, billions of times simultaneously, continuously, without interruption. The internet feels like magic because the engineering that makes it work is invisible. It is buried under oceans, underground in conduits, humming in temperature-controlled rooms, in unremarkable buildings around the world. But it is entirely physical, entirely engineered. And the next time you send a message or load a video, the journey that data takes in the fraction of a second before it arrives is one of the most remarkable engineering achievements ever created.